morning. My name is Habraken and I'm very happy to present you the work where I've performed with Tran Hong Song and Etienne Castillo about the thermal field analysis of solidifying steel shell in continuous casting process. More precisely, we are looking at the thermal field of the mold. So this work has been performed with the help from the Research and Technology Office from Walloon region. So just let us remind what is the steel continuous casting process. You have liquid which is poured in a mold and which is cooled and generate a certain profile. Here it's steel beam blank, but in fact in the research we are more working on not such shape which are closed from beam but on plate. So the important point is that we have liquid in contact with a mold and this mold is cooled down by water. So the model will just be thermal, we don't model the liquid displacement here. And more specifically, we are looking at the sticking breakout phenomenon. Just let's look at what's happened when no defect happens, so it's a stationary state. In this stationary state, you just have the formation of a thicker and thicker shell. So at the beginning you don't have such shell, it's just liquid steel, but very soon under the meniscus, below the meniscus, you will form this shell and it should be thick enough to prevent the liquid to pour out at the exit of the mold. But if you have a sticking breakout phenomena, it means that at one moment you have had a sticking part which stick on the mold. In usual case, the mold is submitted on oscillation, and due to this oscillation, the relative velocity between the slab which is going down and the mold can have maximum and minimum. And in one of the maximum difference between the velocity of the mold and the one from the casting speed, then you can form a crack here if you have a sticking part. Because of the crack, you have liquid steel that happen to be in contact with the mold, and you form a very thin shell here. But as it's very thin, when the slab is going down and you have again a maximum difference between the relative velocity of mold and the slab, then you break again. And so that's how you propagate your crack, and if you propagate it until the exit, then all the liquid steel is going out, and it's what is called the sticking breakout phenomena. And the core business of ABDS is to analyze and measure the thermal field that we have here and deduce from this thermal field warning to the operator in order that they adapt the process feature to prevent such event. So, for instance, there is thermocouples and more specifically optical fiber at different locations within the mold. And you can see that at a certain location A, when everything is okay, it's a constant. But when you have a sticking breakout, then at this level, the liquid steel is in contact with the mold, which is there. And so you have an increase of temperature. And a little deeper in location B, in the beginning you are stationary, you stay stationary a little longer, but the crack has propagated, so you have also a bump. And so Such signature can help you to detect the sticking breakout phenomena. We did model such things in a very simplified way in order to be very quick in the simulation. And so we are just looking at 2D thermal finite element model. It's a Lagrangian code, so we don't model the liquid still movement, and we based our thermophysical data and boundary condition on previous research we already performed on the continuous casting process. So you see here that we work on plate, and our 2D model is in the middle from the width of the plate. You have here the mold. We don't model all the pipe with circulating water to cool down the mold. We just have here at the boundary convection radiation layers of element, and on the opposite we are in contact with the liquid steel and shell formation, and so there we have also a thermal flow which pass through a certain thermal contact resistance. We are in Lagrangian approach, so we have switch off element above the meniscus and below switch on element to model the thermal flow. So you see here that in fact we use a trick. It's the mold which is going up and not the liquid steel which is going down, but from simulation point of view it's correct, easier, and it doesn't change anything on the physics. And to reach the stationary level, as you can see, we have passed all these elements through the mold, and we are sure to be stationary. As you can see here, this is the mold mesh, and on this mesh and in the reality there is different measurement of temperature, and we can check that we reach constant temperature, and of course this model has been validated with a BDS measurement, and for such speeding cast we are indeed in the right level of temperature. So with such approach we are not refined enough at the top when the first crack happens, and so there have been a remeshing step, and we are here with a refined mesh in the top. You can see here to model the crack, we have first this part which will be sticked with the mold. So there will be no relative displacement anymore between the top here and the sticking. They are sticking on the mold. Here we have a crack, and so when we put a crack, it's the user that defines the first crack, but after it's automatic. So the first crack is defined there, and when there is a crack, during the oscillation we introduce new element layers. And these new element layers, they are in liquid steel, and they have the temperature of above liquid here. When do we do this crack? In fact, it's related to the negative strip time. What is it? We have the mold oscillation velocity, and this velocity of course is oscillating like you see here, and here you have the casting velocity. So at some moment during the period you have a higher velocity of the mold than of the slab, and it's at this moment that you have crack event. And the quantity of liquid that you can insert inside the crack during one period is of course limited by the velocity of the casting multiplied by the time period. So it's a boundary. And we can check, of course, that if we look at the mold temperature, we have a maximum temperature that happens because here we have contact of the liquid steel, where other way we have a contact with a shell steel which is already solidified and so cooler. But here, due to the liquid steel, we have a variation of the temperature. And so this liquid steel during a part of the period will solidify, and at one moment, and as we are still applying the tensile effort on the slab, and there is still high velocity during the oscillation movement between the mold and the slab velocity, you will have a new crack. And so the simulation defined here, initial crack defined by the user, and this is the part which is sticked, and where you progressively increase the shell at this moment because it's sticked and always cooled, and then you have the crack which will propagate as shown by the video. Okay, so you have seen, and this is the measurement we can do within this video. We have a marker which are here in our mesh, a certain location P1, and then deeper P2, and even deeper P3, and this P1, P2, P3 correspond to measurement of a BDS, and the measurement that have been done are in good correlation with the simulation value. So when you have a sticking problem and a crack propagation, you have on this P1 you see that the temperature is going down and then up, and if you look at below deeper marker, you see that there is still a little decrease minimum, and then the amplitude of the peak and its shape, they are changing, amplitude is increasing. And that's logical because when you go down, the shell, the solidified shell has been cooled down, so it's cooler. But the crack, it's liquid steel, it's hotter. So that's explain why the peak here is going up. And it has a certain velocity that we can also check with the measurement from a BDS, and also the crack velocity. It's also a measurement that has been extrapolate current knowledge from the industry, and we are within the good range with such velocity proportion of the velocity cast. And the interest of a model is, of course, to use it to do sensitivity analysis. And for instance, we have decreased the speed casting velocity, and we observed, like it is done in the industry, that the crack velocity is decreasing too. And this is one level which is possible with the amplitude and the frequency of the oscillation to slow down and to prevent the breakthrough due to sticking event. You see that the casting speed modify the level of the temperature and of this peak, and modify a little the shape from the waves which go with the crack. I thank you for your attention.